All right, good afternoon, everyone. We'll continue with FETs. And hopefully in the last 20 minutes that we have available, we'll wrap up the semiconductor. Let's see. Okay, so we spoke about the semiconductor device physics that's required to turn on the MOSFETs. We have two kinds of MOSFETs, enhancement mode and depletion mode. Primarily focuses on enhancement mode MOSFETs. Enhancement mode means voltage must be applied, electric field must be created, applied externally to create a channel or enhance a channel. And so in three terminals, we have two main voltages, VGS, and then VDS, and then the output current, ID, drain current. Essentially, what we are doing is we're applying a voltage between the drain and the source. Current flows between the drain and the source, and we control that current by the application of a voltage at the gate. Okay. Now, the device construction itself is symmetrical, but when you buy these manufactured FETs, whether discrete or in an integrated form, one of the terminals, the body terminal is shorted to either the drain or the source, depending on whether it's a what type of MOSFET device it is. So while the physical construction may be symmetrical, the operation would not be. So VGS is the controlling voltage. This creates the channel. And this channel connects the drain and the source, provides a pathway between the drain and the source. So now when the channel is present and you apply a voltage difference or a potential difference between the drain and the source, the electrons or the holes in the channel will be attracted by the opposite polarity charge, and current starts to flow because of the movement of charge carriers. The minimum amount of voltage required to create the channel is known as the threshold voltage, VTN. And VTN is a function of the physical design and the doping profile of the device. Okay. Any application of VGS over and above the required threshold voltage, we refer to that as the gate being overdriven. Hence, that voltage or that potential is known as gate overdrive. Simply mathematical term, simply stated VGS minus VTN, which is what we have here. Okay, so VGS minus VTN, that's the gate overdrive, noted as delta VGS. Now, obviously, below the threshold voltage, channel is not created, so the device is completely off. If there's no channel available, it doesn't matter what voltage we apply between the drain and the source, nothing is going to happen, right? So VGS minus VTN must be positive in order to turn the device on. This is for enhancement mode MOSFETs. For depletion mode MOSFETs, the channel is already present, it's already created. We apply a voltage to actually turn the channel off. So we shrink the channel by applying a voltage, eventually it turns it off. Okay, that's depletion mode. Enhancement mode, delta VGS must be positive. Now, the three regions of operation were triode, active, and cutoff, right? If the voltage is below the threshold voltage, then it's completely cut off, right? It's completely cut off. Nothing is happening in there. So the cutoff region for a MOSFET and for a BJT are similar, okay, right at the bottom of the graph. No matter what drain source voltage we apply, current ID would be close to zero. So when we look at the output characteristics curve, we can see no matter how much we increase the drain source voltage VDS, the current will be very close to zero. So that is cut off. So that's the first region. And the triode region is when you apply VGS, delta VGS is positive, meaning the gate is now in overdrive. VGS is greater than the threshold voltage. And at this point, we apply a drain source voltage, and the drain source voltage is also larger than the threshold voltage. That would maintain the channel at both ends of the device. Right? So if we look here and we look here, apply a voltage between the gate and the source, a channel is created right here that links both the drain and the source together. There's a pathway between the two. Now, if you apply a different potential difference between the two terminals, the drain and the source, electrons will start flowing. All right, drain is held positive, source is held negative with respect to the drain, meaning VDS is positive. If VDS is positive, then electrons are flowing towards the drain. Current is flowing from drain to the source. So ID starts increasing. So far, so good. Okay. All right. So in order for that channel to be maintained, VGS must be positive, and VDG at this end must also be positive. Okay. But the side effect, or the effect, if you will, of applying a positive voltage at the drain would be that we are reverse biasing that junction, because this is P type and this is N type. So if you apply positive voltage at the drain, you're effectively increasing the depletion region at this end. Okay. So before that occurs, before the depletion region completely cuts off the channel, both VGS and VGD are greater than the threshold voltage. And then the current flowing between the drain and the source is linearly related to the applied voltage between the drain and the source. Okay, and so we obtain characteristic that looks like this, linear in this portion. Okay, hence this portion is known as the triode region or the linear region. Okay, in a BJT, this was known as the saturation region. In a MOSFET, this is known as the triode or the linear region. Okay, and then finally, when VDS increases, sorry, not VDS, VGD is below the threshold voltage, the channel is just not extend all the way to the drain. It gets pinched off or cut off. Actually, let's stay away from the word cut off. It gets pinched off. Even though it's pinched off, there's a small gap that is left behind, and electrons that are flowing through the channel before being pinched off will continue to flow at that same rate. The density of charge transmission increases. Okay, so even though you see pinch off, there is still flow of electrons going through. Electrons are injected into that depletion region and swept away into the drain terminal. Okay, so the current now does not increase with increasing VDS. It now maintains a constant value because the number of electrons that are transiting through the channel is now constant. And therefore, we obtain these flat lines or almost flat lines. So current becomes constant. So similar to a BJT, where it behaved as a current source, a MOSFET also behaves as a current source. But a BJT is really known as a current control device because IB, the base current, controls the flow of collector current. Here, it's the voltage that controls the flow of current. So BJT is a current controlled current source, whereas a MOSFET is a voltage controlled current source. So it's two important distinctions. BJT is a current controlled current source, and a MOSFET is a voltage controlled current source. In both cases, you would have almost flat lines at the output. And of course, this occurs when VGD drops below the threshold voltage because of increasing VDS. Okay. All right, let's take a pause. Let me know if you have any questions. Any questions? Okay. Output characteristic of a MOSFET, very straightforward to simulate in LT-SPICE. Pick any device you want. This one had a model number of, let's see, there was a model number in one of the, right here. It should be 2532. Okay. Apply drain source voltage, apply VGS. So you simply take a MOSFET. And here you can see the body is connected to ground, right? So basically it's connected like this. Okay. So the body is connected that way. That means it's not symmetrical because of the connection. Anyway, straightforward enough to simulate the output characteristic. You simply step the VGS voltage. And so here you're applying a certain VGS voltage. In this case, you're applying 2.8. You're calculating what you're not calculating, looking at the output, meaning observing the output. The output right here, where it turns on, or sorry, where it goes into the active region, that's what allows us to create or calculate how much the gate overdrive voltage is. So the threshold voltage is around 2 volts. Applying 2.8, then your gate overdrive voltage is 0.8. Okay. In the next simulation, here we apply VDS. VDS is stepped from 0 to 10 in steps of 0.1 volt each. So about 100 data points. And VGS is swept from 4.5 to 5 volts in steps of 0.5, meaning from 4.5 to 5 volts. You can obtain a set of data curves by simply applying VGS equal to 0, 1, 2, 3, 4, 5 in steps of 0.5 volts each. Have you all used this? Have you all used this input before? Dot step RAM. So basically, you can use dot step RAM to step any quantity. If you want to model a variable resistor, you can use dot step RAM X, and then you can label X as having multiple values. Okay, so you can use this command dot step RAM with multiple different components, including voltage sources, current sources, resistors, capacitors, inductors. And here what we're doing is we're applying VGS 4.5 and VGS 5 volts. So 4.5 to 5 volts, distant step of 0.5. So 2 sets of curves. You obtain one here and one here. And the point where, let's do it this way. So about there and there. I would say that's not quite 1 volt. It's approximately equal to 1.1 and 1.6. But anyway, the point remains that when it leaves the linear region and goes into the saturation region or the active region, that's how you can determine what the threshold voltage is. Okay. So you can take any MOSFET, you can do the simulation. In the lab, you can actually take the MOSFET, apply voltages on the output and the input side, collect your set of data. Once you plot it, you can extract VTN values from your collected data. Okay, so that was the first procedure in that last experiment where you had to extract data from the MOSFET. Okay, and then so final point was turns on here, and so you subtract that from your applied VGS. 4.5 minus 1 gives you 3.5, and 5 minus 1.5 gives you about 3.5. And so threshold voltage obviously should remain the same, right? Does not depend on anything else except the device construction. So in both cases, you get approximately 3.5. All right, transfer characteristic. Transfer characteristic, similar to the BJT out, it is a plot of how the output voltage or output changes with respect to the input. So in this case, since it's a voltage control voltage source, we're going to look at the voltage applied at the input and the current obtained at the output. Okay, so it's a plot of ID as a function of VGS. Okay, output current as a function of VGS. And so how is the input transferred to the output? Okay, and because it's a plot of current as a function of voltage, we come to an important parameter, which is transconductance. Resistance is V over I, Ohm's law, right? V is equal to IR. So resistance is V over I. The inverse of resistance is conductance, G, which is I over V. Transconductance is transfer conductance, meaning how is the input transferred to the output. So input voltage, output current, and it's a ratio of output current to input voltage. ID, the function of VGS. So the change in ID to the change in VGS at the operating point of your device is defined as GM, transconductance. This is not specific just to MOSFETs. It's general electric quantity. Transconductance applies to BJTs also, okay, or for any system for that matter. Transconductance would be change in the current as a function of change in the voltage. There are several different equations and formulae we can use to define or calculate transconductance based on our needs and our design. First one is Kn delta VGS. Second is root of 2Kn times ID. And then lastly, 2 times ID over delta VGS. Okay, Kn again is a constant parameter of transconductance. And we can discuss that in, well, we'll look at, there are a few more slides, but I've made that part of the extra learning or further learning. But we'll end class here for today and we'll pick up here again on Wednesday. So we'll go through a little bit of, transconductance, equations, formula, and then we'll look at biasing and applications of MOSFETs.